biomolecular devices. The nano dimensions of single-wall carbon nanotubes and their electronic properties make them an ideal substrate candidate for anchoring the proteins for biochemical sensing. Integration of carbon nanotubes with proteins by covalent attachment influences the conductance of carbon nanotubes, which are already high. Graphene is even higher. Electron mobility of graphene is quite large, pristine graphene. Now, I'll come to graphene dilemma in a minute. Immobilization, carboxylic acid groups, acid oxidation. We use the EDAC chemistry, stable active esters, N-hydroxysuccinamide, then the amide bond formation. That links the protein with the carbon nanotube. Graphenes are routinely synthesized. The problem with the graphene, lo and behold, zero band gap. How do you switch on and off a graphene device? A graphene integrated circuit was created last year at IBM. Journals are now being almost bombarded with papers on graphene. But producing graphene posed daunting challenges. Then we found that pristine graphene is not helpful because the switching on and off is quite tough. So we want a slightly non-zero band gap. How do you do that? That takes us to the band gap engineering using density function. So, if you put a boron atom there or a bismuth doping, then its band gap is no longer zero. Switching on and off becomes easier. So, we are counting on boron doped graphene, bismuth doped graphene. I still haven't seen in India groups who are doping graphene and producing it. There are one or two groups I suspect are doing it. Now, so the graphene almost euphoria has slowed down a bit, but it's going to pick up momentum too. There's another group in Singapore, Martin Primera, who moved from Tokyo, who is working on graphene synthesis as well. Transfer of graphene for a flexible electrode, this slide is not easily visible. How do we functionalize the graphene? Take the oxide, vinyl ether formation, place in rearrangement, and then create a carboxyl group. This is a general scheme for functionalizing it. Like a carbon nanotube, we use a different procedure as shown here, just a few slides before. Then, once the covalent links are created, we use a number of techniques, FTIR, Raman. By the way, Raman is another abused term. I think Professor Raman will be probably wondering in the heavens, why my name is dragged on into everything. There is Raman microscopy, there is Raman surface enhanced. I don't think Sir Raman ever thought of it. Although I don't know him, he belonged to a totally different generation, and I dissociate myself from that. So, but at the same time, Raman has become a magic word being attached to everything. I don't know how many of them are really Raman. In a meeting in France, we cast a doubt on the surface enhanced Raman. What is it? Nobody knows. There's a lot of mumbo jumbo. Linear scans, excitation responses, that's the basic electrochemical procedure. We looked at the glucose response. By the way, we also use gold. Carbon nanotube, gold and graphene. Gold has become a very important thing in solar cells now. The first biosolar, quantum dot, biosolar, hybrid solar cell will be gold. And eventually graphene. Would the graphene prices come below the gold prices? We don't know. If graphene prices are so high, then I think the London metals market should consider graphene. Fundamental changes, chaos can occur in the world of economy. And graphene may have to be traded. It may even become an object for dowry. We don't know at this point in time. Somebody demanding we need about 1 kilogram of graphene. These are some potential, this is the cholesterol concentration. I'm not going to, I don't know how much time I have. I have a flight to at 4:30. I'll see what I can do on the results. There are tons and tons of slides, and Dr. Sundaramurthy is going to be talking and some linearization from an electrical engineering point of view. Frankly, the mathematicians are difficult for me to understand. We just got a paper in physical reviews. Please don't look at it. Avoid it the same way you will avoid Limburger cheese. There are 47 equations. Blind operators, jump operators. Finally they come up with an efficiency. You have to believe them. It's in Physical Review B and just about a few days ago. I'm a co-author that I tried to go through line by line by line. At some point I got totally turned off. And similarly, what he's talking is also mumbo jumbo to me. I need to sit with him. Now comes the microfluidics. Things we never thought before. Of course, there's a nanofluidics, there's a picofluidics, I'm sure there will be a femtofluidics, and we'll go to septo. At some point, we're going to divide things that we cannot divide them any further. I suspect the smallest particle might very well be the soap. Now, the day we catch it, if there is something called a soap, it may not be. So, into thinking and philosophy and Vedic studies, I think, have tons and tons and tons of things, and we're ignoring them. Flow of a viscous fluid like blood requires understanding and manipulating the microfluidics. This is where the Sandia laboratories comes in. To ensure the efficient functioning of the desired biosensor, microfluidics provide an understanding of the behavior, precise control and manipulation of fluids that are geometrically constrained to a small, typically sub-millimeter scale. Why is it important? If the blood, a viscous liquid, it's a small flow. The blood has sometimes other debris in it that has to be also filtered. Now, on the fabrication of the devices, we have relegated ourselves to Koreans. They are one of the excellent device fabricators. Now, this is a diagram of the electrogeometry, assessment of the microfluidic device. It's quite complicated. I am not an expert in this. I'll show you a few slides. Any questions on this should be directed to my collaborator at Han Yong. I think in future, in all these presentations, we must be able to bring all of them on a large TV screen so that questions can be fired at them. This is the process flow of the device fabrication. There's a lot of technical details involved in this. This is a schematic of a microfluidic device. They are posing daunting challenges. This is a schematic of a microarray chip, the one that we use in the smell receptors. We have taken the smell receptors and created a microarray chip. This is how a fabricated device may look like. There are a lot of data here, and using gold platform with cholesterol, with glucose. At this moment, carbon nanotube based glucose sensor. What is the accuracy? We think it's about around 5%, 4 to 5%. We are not yet published. We have a prototype sitting. These days, we are dictated by the market, not by the availability of a protein to do some biophysical studies. So, if there is a demand, look at the demand, reverse engineer back into basic science. That will ensure those of you who are contemplating jumping into software to see that there is a future here, there is money. Spin-off companies in India, although there will be a lot of debacles, I am sure we have tons and tons and tons of debacles, will eventually create money in the hands of scientists, in addition to the salaries. That will be an incentive to draw younger generation into that. Now, how does this prototype micro-scale device look like? Compartment introduce and remove a disposal chip that accommodates microchambers with multi-channels, a micro pump for the reader, and it requires only a few microliters for detection. The chip contains filtration and electrochemical reaction, microchambers which are interconnected through microchannels, sensors are several field effect transistors, channel of which are pre-functionalized semiconducting single-wall carbon nanotube or graphene, doped graphene, and will be operated in backgated mode. Each covalently anchored protein would be sensitive only to a particular targeted species. When the targeted species interacts with the proteins, electrochemical reactions happen. Conductance and FET changes, which is eventually that will be detected. The ease in functionalizing single-wall carbon nanotubes and graphene, doped graphenes to detect desired species compared to other nanowires makes the detection species at the parts per million level. So the sensitivity, we can bring it down to 4 to 5%. We are still repeating the experiments. I don't want to say it for sure. It should be not 10%. Conventional microfabrication and state-of-the-art directed assembly methods will be employed to fabricate the prototype devices. The electrohydrodynamic micropump would be integrated into the micro sample holder. The filtration chamber consists of single wall carbon nanotube separates out the cholesterol and the lipoproteins from the background